So I want to talk to you about calculating pH for strong acids and bases, especially about the sig fig rules and using your calculator to do that. So you've already learned at this point about the pH scale and about calculating pH. And you've probably seen various versions of, like, here are some common pH examples. So there are three important equations having to do with acids and bases that you are going to need to know and that we will be using during this lesson. The first one is that very calculation about what is pH. pH is, is found by doing negative log the hydronium ion concentration. Now, I know we don't use logs that often, kind of outside of science, and so it's really easy to forget what they mean. But what we're saying here is that 10 raised to the negative of this power equals that. So we can actually rewrite that as this. The hydronium ion concentration is equal to 10 raised to the negative whatever the pH is. And that's really useful because I can use both of these depending on what I want to find out and what I have. If I'm given the hydronium ion concentration and I want to find the pH, then I want to use this version. If I'm given the pH and I want to figure out the hydronium ion concentration, I use that version. And what if I want to know hydroxide ion concentration? Well, then I have to go back to the equilibrium constant for water, because the molarity of the hydronium ion times the molarity of the hydroxide ion, regardless of what the pH is, will always multiply together to be 1.0 times 10 to the negative 14. So these three equations allow me to calculate pH, hydronium concentration, or hydroxide concentration, depending on the information that I've been provided. So let's do that. Let's take a look at this first problem here. What is the pH of a 2.5 times 10 to the negative 4 molar hydrochloric acid solution? So it's asking me for pH. What is pH? So when it's saying what is pH, I want to use the pH equals equation. So pH equals negative log of the hydronium ion, or hydrogen ion if you prefer for simplicity, the hydronium ion concentration. So you might be looking here and going, well, they didn't tell me the hydronium ion concentration. Actually, they did, because hydrochloric acid is a strong acid. And remember, when we talk about strong versus weak acids, what we're really talking about is the reversibility of the reaction, the degree to which the forward reaction occurs, or the percentage to which they dissociate. Depending on how you look at it, we're all saying the same thing. So since hydrochloric acid is a strong acid, that means it 100% dissociates. It's not really a reversible reaction. So if I have 2.5 times 10 to the negative 4 moles per liter HCl, and it's 100% dissociated, I also have 2.5 times 10 to the negative 4 moles per liter of hydronium. So the molarity of the acid is the same as the molarity of the hydronium ion, assuming it's a strong acid. And in this class, we're not going to worry about what to do when it's a weak acid. We won't be doing those calculations. You can save those for a future chemistry class if you pursue chemistry and biology in your future. So from there, I want to do pH equals negative log, and then I'm, that value, 2.5 times 10 to the negative 4, the hydronium ion concentration, right there. So you need to get familiar with your calculator, or the calculator that you're going to be using, and make sure that you have one. Most calculators do, a scientific calculator, have that logarithmic function. So I want to show, I have a little video of how I do it, what it looks like on my calculator. So I'm going to show you two different ways. You might not have an identical calculator to mine, but you might have one similar enough that you can still kind of figure it out. Either way, you want to make sure that prior to taking any tests for this content, that you practice with the calculator or a similar calculator that you'll be using. So watch as I solve this problem, and I'm going to do it in two different ways. So negative, and then I have a log button. It just says log, 2.5. And then I use that second button because it's allowing me to use that little, it's an EE, or it looks like an E, and it means times 10 to the, and then I put in -4. And when I put in equals, I get that value right there. So let's write that down because I am going to show you another way. pH equals, we'll talk about sig figs in a sec, so I'm just going to write down as many of the values as I can. That should be good enough. So again, there's my negative button right here, log 2.5, and then this little second button on my calculator allows me to, that these buttons will do the thing above that's in yellow. And so that it stands for that exponent here, that times 10 to the, and then I just had to put into the -4. But here's another way to do it, and you'll see I get the same answer. So rather than using that second button, I do negative log 2.5 times 10, and then that upward caret means like raised to the, makes it a superscript essentially, -4 parentheses equals 3.6. So it didn't matter which of those methods I used, I got the same answer. So familiarize yourself with your calculator. Now, we got to talk sig figs. What sig figs is it? Is it 2 because that's my weakest link here? Well, that's what would be nice, wouldn't it? But my last gift to you is a weird new sig fig rule, except I didn't make it up, so you can't be mad at me. So when it comes to logarithmic functions, the sig fig rule is like this weird mix of the addition and subtraction. It's completely new and not one we've seen before. The total sig figs in the concentration, so that's in your molarity concentration, is equal to the number of spaces past the decimal in the pH value. Okay, so let's do an example so that we know what I'm talking about. So let's say my hydronium ion concentration is, we're going to do really simple ones so that I don't have to use my calculator, is 1 times 10 to the -6. And that's how that's molarity, moles per liter. That's how concentration my hydronium ion is. So what's the total number of sig figs in that? Well, it's 2, because trailing zeros are significant with the presence of a decimal. So 2 total sig figs. So what that means when I go to do the pH, so the reason I said this is simple is when you have a number this nice, this so perfectly 1.0, not 1.5, not anything like that, the negative log of it is the same as this. It's this number. So the pH is 6. That's why I was saying it was nice and simple. I can even do that in my head. However, I don't go, okay, 2 sig figs. I go 2 places past the decimal. So 0.00. So the total sig figs in your concentration becomes places past the decimal in your pH. Decimal. For the pH value. So 2 total becomes 2 places past the decimal. And if I were going the other way, I would actually do the same thing. I would go 2 places past the decimal gets to be my total. So these go then like kind of back and forth in that way. So let's look back at that problem then to determine our number of sig figs. So if I look at concentration, my total concentration, you'll see that here I also have 2 total sig figs. But that isn't going to be 2. I go 2 places past the decimal right here. So my pH is 3.60. My final answer. Now, I always like to ask myself, like, does that make sense? Well, this is an acid, so I would expect its pH to be below 7. Yeah, that makes sense. All right, so moving past the pH, that one, let's go to, what about if it's a base? What is the pH of a 3.2 times 10 to the -3 molar potassium hydroxide solution? Now, let me tell you what I know a lot of students want to do. What I myself would very likely do is I would do exactly what we just did. And I would do negative log 3.2 times 10 to the -3rd. And you know what I would get? I would get 2.49. However, let's stop and think about this for a second. Is that an acid? Oh, heck no. That's a base, right? But this is a really acidic value, so what did I do wrong? Well, this value given here is not the hydronium ion concentration. It's the hydroxide ion concentration. That's what it's given me. Because it's a strong base, the value of the molarity of the strong base is the same because it 100% dissociates. So I get 3.2 times 10 to the negative 3 moles per liter of hydroxide. But that's not what pH is. pH is negative log of hydronium or hydrogen ion. So what I need to do is I need to solve for hydronium. So how am I going to do that? So you remember, Kw, we're going to use the equilibrium constant. Remember, the equilibrium constant for water, which is 1.0 times 10, to the negative 14, is equal to the hydronium ion concentration times the hydroxide ion concentration. Well, if I know one of those, if I know this, then I can solve for that. And I would do that by 1.0 times 10 to the negative 14 divided by 3.2 times 10 to the negative 3 will equal the hydroxide value. Whoops, sorry guys, we already know the hydroxide value, the hydronium value, because that's me putting in this value, dividing both sides by it. Now, I want to do the same thing. I want to show you how you can do this on your calculator, and I'm going to show you two different ways, and then I'm going to show you a way that will get you the wrong answer because this is a pretty easy mistake to make. So I'm going to start with parentheses 1.0, and then the second button to get that E, because remember it means times 10 to the negative 14 divided by parentheses 3.2, so I'm putting in the molarity of the hydronium, second, raised to, that E button, raised to the negative 3, parentheses, and equals. So notice what I get, 3.125 times 10 to the negative 12. So another way, 1.0 times 10 to the times 10 caret to the negative 14. So I'm kind of doing the same thing I was in the other one, where you don't have to use that second exponent function if you don't want to. Let's see if we get the same answer. We're going to, guys. I pre-recorded the calculator. And we do. All right, so let's pause it real quick because I want to write that down, because there's, a 0 chance I'll remember it correctly later. And now I want to show you what happens if I do one other thing. Okay, what am I doing differently? I'm not using the parentheses. I'm not putting the parentheses around this. Now notice, I got the same overall number, but a totally different exponent and a completely incorrect exponent. So most calculators are going to really require those parentheses in order to get the correct answer. So this actually isn't the answer to our problem, though, is it? Because what this is, do you guys even remember? It's been 100 years since we started it. This is just the hydronium ion concentration. Now I need to take the negative log of that value. I like to keep all my sig figs till the end and deal with that. Then the negative log of that value is 11.51. And the reason I have 2 places past the decimal is because I had 2 total sig figs in my original. Does that pH, is that making more sense? Yeah, that's a pH of a base. So when you're calculating the pH of a strong base, you have an additional step you need to do, because you need to find the hydrogen